about all the kind of correspondence and the type of applications of SUSY. So please welcome Ito.
Thank you very much. I'd like to thank the organizer for inviting me to give the chance to talk in this very nice conference. I'm Katsushi Ito from Tokyo Institute of Technology. I'm going to talk about ODE correspondence and its application to supersymmetric gate. So this work is in collaboration with my former graduate student Christopher Locke and present graduate student Humphrey Xu. And it's mainly based on the first two papers, but some later published that in work in progress. So first I explain some introduction, begin with introductions. The ODE correspondence is kind of a relation between some spectral analysis approach of the ordinary differential equations. And it's actually related to some functional relation in quantum integral method. Functional relation, I mean Bent-Anderson equation and other functional relation to solve necessary to solve the quantum integral systems. So it was proposed by ODE and Tateo in 1998. So this can be regarded as a very non-trivial correspondence between classical soliton equations and quantum integral systems. That's very mysterious relations. So actually, Gray and Tateo in 1998, they studied this kind of Schrödinger type equation. This is the second order differential equation with potential x2 to m. So they found that the spectral of this analysis of this the solution of these equations, and find that the its relation to the a2m minus 1 type sound dynamic beta equation. So they also extended to the this Schrödinger type equation to the higher dimensional ordinary differential equations, the other type of the integral modules. So this is a kind of phenomenology, but in 2010, Lukyanov and Zamorozhkov find another type of ODE correspondence. So they studied some Shinsh-Gordon equation. This is a very well-known classical integral equation type. They studied the linear problem associated with this soliton equation. So it is formulated from the Lux representation of this Shinsh-Gordon equation. So they find that it's actually the linear problem and relation between the linear problem and the quantum integral models. So actually they found some functional relation appearing in some quantum XXD model or 6-part X models. So they also found taking some limit, I call it a conformal limit. These relations reduce the ODE above ODE correspondence found by Gray and Tateo. So this suggests some existence of some certain real algebra structure behind this ODE correspondence.
So the linear system is whose order?
First order differential equation with higher rank. So motivation of this my work is to understand some mathematical structure of the ODE correspondence, and it's physical meaning. It's not physical meaning is not clear at present to me. But so we want to make some complete and complete dictionaries between two models. What kind of ODE corresponding what kind of integral models? So what making us try to making up some dictionaries based on some algebraic structure. So this correspondence may be useful to understand the relation between integral models and some meaning in the classical solving. So it also have some application to the some physics in case studies. One major example application of this example is some ADS CFT correspondence. So the physical object, like a gluon scattering amplitude and form factors and correlation functions are formulated in terms of this kind of Cauchy equation in the upstream tablet. It was realized in the minimal surface, so its shape is satisfied the Cauchy equation. That's an area of the minimal surface related to the free energy of the related quantum integrals. That's some recent direct application of this ODE. But in this talk, I'd like to talk another application of this ODE correspondence. I'm going to apply this approach to the some Welfare gauge correspondence, which appear in the low energy effective theory of the quantum field. So in this talk, I will introduce some basic concept of the ODE correspondence with taking some Schrödinger type examples, and and also in particular I'm going to talk about its application to the n=2 superpattern quantity. So it's called RBS Douglas. That's my content of the talk. Okay. So I will talk about this subject, and first I explain some ODE, what is ODE correspondence, and how to understand the ODE correspondence from the viewpoint of affine philosophy. This is an extension of the Cauchy equation. Then I will apply this correspondence to the RBS Douglas system. Okay, so I will start from the Schrödinger type equations, but I add some angular momentum potential x, 1 over x squared potential. But different from the ordinary quantum mechanics problem, x is some complex, regarded as a complex variable. It's defined on the whole complex, not the real positive. But so energy also should be regarded as some complex parameter. And so we are considering some general two-dimensional ODE problem in the complex way. L and M, maybe M is regarded integer later, but L and M are some real number. M is some positive value. So we consider some solution of this linear differential equations, and but it's difficult to solve without some particular cases, like m is equal to 1. It's very difficult to solve in this form, and if we can solve it approximately at some typical region in the complex. So one is the case the x is very large, and we first consider the solution along the real positive line, where the x is very large. So we have two kind of solutions. one is the expanding solutions along the real axis. The other is the decreasing solutions on the real axis. So I write down some decreasing solution along the real line. So it can be obtained by the kind of WKB analysis of this differential equation. So so this is the solutions uniquely defined along the real axis. So we have also another divergent solution, but it's not unique. We can add arbitrary arbitrary small solutions to the large solution. So this small solution, we call it subdominant solution, is unique in this real axis. And actually, this is the solutions, decreasing solution, with some this sector, angular sector in the complex. So
you set boundary conditions
yeah, I'm saying by some boundary condition.
like quantum mechanics.
Yeah. So some particular value of energy, so it's reduced to some ordinary quantum mechanics problem. Thus, so we have now always this potential has bounded solutions. So the two solutions are always decreasing at larger. But in general, we have two types.
So E is not discrete, or is it?
It's continuous parameter.
Continuous.
So on the other hand, for small x, where x is around 0, so this is not dominant part of the potential. The divergent part, angular momentum part, is the main part, main contribution for the solution. We can solve it in a approximately by power series solutions. And the leading term is just we have some quantum mechanics answer.
X equals 0 and the infinity are the only special point.
Yes, we see that we have no other singular point on that potential. But we change the potential, we can have another singularity. That's very difficult. But it appears in the ADC of details.
The solution does not depend on E.
Well, it depends, but just the reading, we just write the reading.
It's confusing at large x because if m is 1, it's just harmonic oscillator, right?
Yeah, that's right.
And the coefficient of the exponent is the Hermite polynomial,
Yeah.
whose rank depends on
Yeah,
energy
it's,
level.
but it's some, in that case, it's, E is some proportional to the some times n plus 1 or 2 times some oscillation. But we have general, in that case, general E. It's not given by the Hermite polynomial. That's the situation, I think. So what the general solution for this problem is we see that this ODE has some invariance under the rotation in the complex plane. So we scale the x into AX with A being some constant, and at the same time the parameter E is changed to A to the n. So the differential part and the potential part change in this way, and the solutions, the argument of solution also changes like this. If the A is chosen that the root of 2m plus 2's root of the unity, that equation becomes different. So invariant becomes invariant. So we have so I want to choose the m is to the integer later. So in these cases, we have generate the other solutions by this phase rotation of the original solution defined on the real axis. So actually, this is the convergent range of the solution. It changes due to the disk rotation. So actually, this is called some in our terminology semantic rotations. So semantic rotating solution is a subdominant in the different angular set in the complex. So actually, this is the Y1 is the divergent with the divergent solution in the real axis. So we can take a basis of this differential equation, the neighboring solutions in general, yk and yk plus 1 forms a basis of the solution. So we're sometimes taking Wronskian for these solutions, which are defined by this. And if the f and g are solution of the differential equation, it is their Wronskians are constant due to the that we can take a derivative of this. We can check this is constant and independent. And it has anti-symmetry. And due to the sum, we define wk1 and k2 is the Wronskian of the yk1. So we take some certain normalization. We know the explicit formula of the y0 and y1 at the large x. So then we can take its Wronskian and take some appropriate normalization of this solution. It is shown to be constant, and we normalize it to be 1. And also we have taken semantic rotation. And so it is shown that its Wronskian is related to the not shifted one, but the argument of E is some rotated. So that means the neighboring solution of the two solutions are shown to be 1 in the present notation, which is also independent of E. So now we take some special basis, y0 and y1 as some fixed basis of that solution. So every solution of semantic rotated solution is expressed in terms of y0, a linear combination of y0 and y1. So actually it's expressed in terms of Wronskian. So we define some the t function by the ratio of this Wronskians. Actually, we normalize W0 to be 1, but this is some general ratio. And we have some shift of the argument, which sometimes appears. We define the shift of the argument of E, rotation of argument E by this notation. So we define some key functions, and we know that every 2 by 2 determinant matrix of determinant of matrix satisfy the kind of relation. It's called some critical relation. So actually, we use this combining these key functions and relation, critical relation. We'll find the key satisfies some function relation. So this is the form of like this, and this is called actually in the context of integral models, it's called the T system. Then we define the product of key functions. We define the Y functions, and they also satisfy the function relation. It's called Y system. So this is some popular typical function relation satisfied by some quantum integral system. So we obtain from that conditions, the function relation. So, but we have some infinite number of t functions from here. But in some simplest cases, it is reduced to the finite t system that appear in the that is the situations we can make it relation to the some quantum nuclear system. For generic situations, M and L, we remember T is proportional to the Wronskian W0 S plus 1. So it is obvious that the same solution, Wronskian same solution vanishes. So WT minus 1 is there. We have normalization that T0, W01 is 1. So this is gives me some normalization T0 is equal. So it's a general boundary condition for the sequence of T systems. But in the case of the special parameter, we have the infinite T system is truncated to finite. So I will consider this type of the second type. So L is equal to 0 and 2n plus 1 is some integers. So in this case, the plane of the subdominant solution are covered by the finite number of regions. So after some rotation, we back to the same Stokes region, angular sector. So that means we have some T system is truncated at some integer. So we have finite type sequence of the relation of the finite sequence. So it is called the we have A n minus 2 type T system. But in general, L is not equal to 0. We have some much more extended T system. I will not discuss here. So we have also another function relation from this ODE, which makes it, if we consider some the behavior of the around the origin. So we have two solutions. One is x to the L plus 1, the other is proportional to x to minus